All right, well, hello everyone. Um, Going to go through some key points of this section of notes, which is talking about understanding the value of a logarithm. So this first thing here that's pretty important, um, log base b of a, b has to be greater than 0 and a has to be greater than 0 as well. A lot of times you will hear me refer to a keyword being the argument. The argument is basically the inside of the logarithm. So if you do hear me talk about the argument, that's what I'm talking about. So this first section right here is kind of get a good idea of being able to go from a logarithm to an exponential equation. So they're tied pretty closely hand in hand. And you should be able to take an exponential equation and rewrite it as a logarithm, and take a logarithm and rewrite it as a exponential equation. So all of these examples are going from logarithms to your exponential equation. It's like log base 3 of 27 is equal to 3. That is rewritten as 3 because that's the base. There it is right there. And then to the third power is equal to 27. 2 to the fourth is equal to 16. Log base 2 of 16 is equal to 4. So the base of your logarithm is going to be the base of your exponential equation. The answer after the equal sign is your exponent, and then your argument, which is the inside of your logarithm, is rewritten as the answer of your exponential equation. So there are just awesome examples of being able to take a logarithmic equation and write it into an exponential equation. So those are pretty simple. And it kind of gets into a little bit of some basic things. That's basically, this right here is basically talking about the same thing I just said. Log base b of a is equal to the power / exponent to which the base b is raised to equal the argument a. And then there's three things that they kind of talk about based on the examples that you see up there. If a is equal to b, then the value of log base b of a is equal to 1. That should make sense because if you have a base raised to the first power, you're going to end up equaling exactly what you had to begin with. Like 3 to the first is 3. 5 to the first is 5. The second one, if b is less than a, then you know that the value of your logarithm, log base b of a, is going to be greater than 1. And then if b is greater than a, then you know that the log base b of a is going to be less than 1. So here on the next page, the top part is talking about the common logarithm. If you look at a calculator, if you go to type in a logarithm into a calculator anywhere, a lot of times it'll just say log and that's it. There's no really base that's being shown. That is the common logarithm. So anytime you see a log that's just log by itself, it's really log base b or log base 10. But they just normally just don't write the 10 because it's the common logarithm. So right here, this would be like log base 10 of 5. So 10 to what power would give you 5? Approximately 0.699. Here, log of 100, I could rewrite that as an exponential equation. And we'll try this right here. And that would really be rewritten as 10, to what power is equal to 100. And that's why the answer to that logarithm is 2. This next section down here, get rid of this. This is one of the sections that shows up in your homework. They basically are asking you to estimate the value of a logarithm in between two integers, if you can. So like these first two, I don't have to estimate it in between two integers, just basically because log base 3 of 81, if I were to think about that, 3 to what power is equal to 81? The answer to that is 4. Log base 2 of what power is equal to 1/8? The answer would be -3. So it also talks over here that you can evaluate a logarithm that has, log base 3 of 81 using a change of base formula. So you just take the common logarithm of 81 right here and divide it by the common logarithm of 3. Log base 81 or log of 81 over log of 3. If you type that into your calculator, you're going to give you 4. This is probably more so the change of base was really important because a long time ago, with some of these graphing calculators that we had, you didn't necessarily, when you typed in the logarithm, if you wanted to type in and actually figure out like that answer, you would have to actually type in log of 81 divided by log of 3. Now with your graphing calculators, a lot of them, when you hit the log button, it'll say log and it'll put a box right there and it'll put a box right there. And if I wanted to evaluate log base 3 of 81, I would just put 3 down here in the base and I would put 81 in the logarithm or in the argument. And then I would type enter and it would give me my answer. Not sure if Desmos would do that or not. Let's go find out real quick. If I go to Desmos, let's see. I want a scientific calculator. So logarithms in here. There we go. There's log. So in this case, if you're using Desmos, if I wanted to find log of, log base 3 of 81, it does not give me that option to be able to type directly into the base and to my argument. So I would have to, if I was using Desmos, rewrite it as log of 81, divided by log of 3. And then you see there, it gives me my answer as 4. So some of those calculators, some of the newer ones, when you type it in, will automatically kind of allow you to type in the base and the argument to get your answer automatically, but not Desmos, apparently. All right, so back to this right here. So if I get down here to the third example, log base 2 of 9, if we think about that, 2 to what power is it going to equal 9? 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16. So it doesn't come out as a whole number. So when they are asking you to find the value of the given logarithm, if the value is not an integer, between what two integer values do you think the value of the logarithmic expression lies? This is what we're talking about. So like I know 2 cubed is 8 and 2 to the fourth is 16. So log base 2 of 9 would have to be in between 3 and 4. Some type of decimal to actually get it to equal 9. 2 to what power is 9? It's 3 point something. So when I use Desmos, if I needed to, or your own calculator, if I want to actually evaluate log base 2 of 9, I'll type in log of 9 divided by log of 2, and there it is. There's my answer. It says that it's 3.170, which we would expect because 2 cubed it was 8 and 2 to the fourth is 16. And really, if I keep thinking about it, like 9 is closer to 8 than it is to 16. So my decimal should probably be closer to 3 than it is to 4, which it is in this case. Then just give you 3 more examples here. Log base 3 of 36. 3 squared is 9. 3 cubed is 27. 3 to the fourth is 81. Well, 36 right there is in between. It's in between 27 and 81. So I know that the answer to this logarithm has to be 3 point something. 3 point something. And once again, I'm probably thinking like, hey, 36 is closer to 27 than it is to 81. So my decimal should probably be closer to 3 than it is to 4. It's got to be probably less than 3.5. And if you use your change of base formula, log of 36 over log of 3 ends up being 3.262. So they just give you a couple examples, and then they go down here and they talk a little bit more. Erase all this stuff real quick. They talk a little bit more about that change of base formula. Log base b of a. If you wanted to rewrite that with the change of base formula, it would be log of a over log of b. And if you're using Desmos, you'll definitely have to use that change of base formula. So then they kind of get into developing the natural base of E. E is a unique number. It is very much like pi, where it's an irrational number. And this expression over here, 1 plus 1 over n to the nth power, the larger number that you plug in for n, the closer that you actually going to get to that exponential number, e. Okay. Now, the thing is with e, if you pay attention right here, log base e of a. Anytime we're using e as our base, we're not going to write it as log base e. We're going to use the natural log expression, which is ln. So that's where that came up from. You can see it on your calculator. Normally, the natural log button and the log button are pretty close to each other. And the same properties that exist with logarithms are going to exist with the natural logarithm as well. So that's a little bit about the common logarithm. It's just a little unique in terms of the value. It's kind of like, like I said, it's kind of like pi. Okay. So then I just give you some more examples in terms of rewriting a logarithm. I want to get down here to the equations. I'm going to try to keep these notes sections a little short because you guys can always rewind and go back and rewatch it. And I want to bog you guys down with watching lengthy videos of me talking or anything like that. All right, so solving logarithmic equations for right now. I'm just going to talk about each one of these examples real quick. Mainly the idea is with a logarithm equation, a logarithmic equation is if you can't figure it out with a logarithm, the best idea is to try to rewrite it as an exponential equation and then solve your exponential equation from there. So we just got done talking about exponential equations in our last unit. So kind of thinking back about some stuff that we talked about, rewriting both sides of your equation as the same base. So that way you could drop the base and you just set the exponents equal to each other. That's kind of the idea here when we're talking about, hey, here's a logarithmic equation, rewrite it as an exponential equation and then solve it. So here, this first one, log base 9 of x is equal to negative 2/3. If I were to rewrite that, my base is 9, my exponent's negative 2/3, and it's equal to x. At this point, this problem is basically solved because it says x equals, and that's kind of the goal, is to get x to be by itself. But then they just went through and just kind of simplified this. So, the negative exponent, the fact that it's a negative fraction, you take the base and you flip it, and now the exponent becomes positive. And then they're just rewriting 1/9 to the 2/3 and it's kind of simplifying it down to the cube root of 1 over 81. Next example over here, the natural log of x is equal to 3. If I were to rewrite that, my base of that logarithm is e, so I'd have e cubed is equal to x. Done. That was easy. X is by itself. I'm going to leave my answer in terms of e in that case because it's more exact. You could take e and raise it to the third power and type it out and get your answer. It's just going to be a decimal. But if you take an irrational number and cube it, you're still going to have an irrational number. So leaving it in terms of e is going to be more exact, which is preferred. The next example right here, log base 3 of 2x plus 1 is equal to negative 3. First thing I would do is rewrite it. So 3 to the negative third power is equal to my argument, which is 2x plus 1. And then they're just going through the steps there to solve. 3 to the negative third power is 1 over 27. You would do 1 over 27 minus 1, and then divide by 2, or in this case, they multiplied by 1/2, and there's your answer. This one over here, you'd have 25 to the x power is equal to 5 radical 5 when you rewrite it as an exponential equation. So this is the first one. Really going to have to try to rewrite both sides so that way it has the same base. So like I could rewrite 25 as 5 squared. So then you have 5 squared to the x power multiply the powers because you have a power raised to a power. You end up with 5 to the 2x power. On the right-hand side, 5 times radical 5, square root of 5 is rewritten as 5 to the 1/2 power. So you have 5 to the first times 5 to the 1/2. When you are multiplying two things together with the same base, you add the exponents. So we end up with 5 to the 2x power is equal to 5 to the 3/2 power. And you'd want to drop the base out of the equation at this point and set the exponents equal to each other. 2x is equal to 3/2, and then they just multiply both sides by 1/2. And then there's your answer is 3/4. So the two other examples here. The bottom left-hand one's probably the most difficult. We can go ahead and talk about that one real quick. When you rewrite that one, becomes my base is 2 of my logarithm. So I have 2 to the x plus 2 power is equal to my argument, which is 9. In this case, this was one of our problems that there's no way that I can rewrite both sides of my equation as the same base. 9 cannot be rewritten, so it has a base of 2. So at this point in our logarithm unit, you will not be able to solve this algebraically. So this is one where you're going to have to solve this graphically, which means you need to graph 2 to the x plus 2 power, and then you also need to graph 9, and then you're looking for the points of intersection. The points of intersection on your graph. That would be the easiest way. And then down here, they even actually talk about like, hey, I could actually start with my logarithm right here at the very beginning, log base 2 of 9. Let's rewrite it, because really all I have to do to get x by itself is just subtract 2 from both sides. So whatever log base 2 of 9 is minus 2 should be my answer. So they just used the change of base formula, log of 9 over log of 2, got 3.170, and then subtracted 2 from it. And then once you look at that, the answers are exactly the same. The intersection point and then the answer are exactly the same. This last one here, if I rewrite it, remember the natural log base is e. So I have e to the 5th power is equal to my argument, and then I'll just subtract 3 from both sides to get x by itself. And remember, I'd want to keep it as e showing up in my answer just because that's more exact. All right. So that was the notes for understanding the value of a logarithm. So day 55 homework is the one that is tied to this. Getting ready to look at the next section of notes and post that as well. And that'll probably be posted here in a couple of minutes. But really, day 55 and day 56 homework, just a reminder, those are due by the end of the week, and this is all we're doing this week. Next week's spring break, which I want you guys to take off and relax. Don't do any schoolwork and just enjoy a week. I guess being at home and doing a whole lot of nothing. Try to go on walks or something like that, and just be safe. But thanks for tuning in, and I'll start filming this next lesson here in a minute.